the virtual floor to him. So our second speaker is Professor Emilio Martinez-Paneda. He's an associate professor at the University of Oxford. And prior to joining to Oxford, he was an associate professor at Imperial College London, where he led an interdisciplinary research group from 2019 through 2023. And his research spans a wide range of challenges at the interface of mechanics and other disciplines such as biology, geology, chemistry, and material sciences. But he's mainly focused on computational mechanics. So with that, I guess I'll pass the virtual floor to Emilio so we can hear his talk.
Very much, Pania. Can I confirm that you're all seeing my screen, full screen?
Yes. Yes.
Thank you so much. Yeah, thanks a lot, Pania, for your very kind introduction and for arranging this. I'm really happy to engage more with the US Association for Computational Mechanics and heavily involved in various associations in Europe, like the UK, the Spanish one, and the wider ECOMAS, but I haven't interacted that much with the USACM, so I'm really keen to do that for the forthcoming future, and yeah, very happy of this opportunity. And yeah, thank you all for being here. As you heard, my name is Emilio Martinez-Paneda, and the title of my talk was Unlocking the Challenge of Simulating Corrosion Through a New Facial Revolution, as you can see there, or towards a virtual corrosion lab. And I think this topic motivates itself. So you all know that corrosion is as a humongous problem. It's a problem, I would like to say, everyone's problem. So only in the UK, as you can see here, we spend more than 46 billion pounds in corrosion failures per year. This is the annual cost. So it's really a massive problem that has a massive societal cost that is has been labeled the biggest threat to the durability and sustainability of materials, that often results in catastrophic failures, and more importantly, that has long eluded scientists and engineers. Despite all our efforts, we are still unable to predict these catastrophic failures. So it is, I guess, a problem. We have learned a lot, of course, through decades of experimental corrosion science, but we have not been able to incorporate that insight into a model. So it's a problem that has eluded, in particular, computational scientists. And as a result of that, we lack predictive models. And as a result of that, we are seeing these catastrophic failures occurring every day more frequently than the day before. And, across the entire world, in well-developed countries with well-established engineering standards. And there's multiple reasons why, we are still unable to predict corrosion failures despite decades of research into this area. I think one of the reasons is that often the conditions under which we run our experiments are very different to the conditions under which we try to predict or the conditions under which these catastrophic failures happen. This is a classic experiment, a classic example that is illustrated here. So on the y-axis, you have something like time to failure. And on the y-axis, on the x-axis is a measure of the severity of the environment. It could be the corrosion current density, for example. And this is typical, for example, of accelerated experiments on reinforced concrete structures. And basically what you run is some sort of experiments where you have a very aggressive environment where you prescribe an accelerated corrosion current density, so your experiments don't last forever, and therefore you obtain data in this area here. But then what you need to do is to predict what's going to happen in this regime here, where these catastrophic failures will occur over periods of decades. And of course, we cannot run experiments over decades, so going from here to here is a challenge. Of course, you can always interpolate data, and to a certain extent, you could argue that computer models have always existed in corrosion, in the sense that there's always been experimentalists that, run a few experiments, draw a line through those experiments, they pick their favorite polynomial, and then they come up with some sort of empirical or phenomenological law where they say, okay, my time to failure is related to corrosion current density through some magic parameters, some empirical parameters, alpha and beta, which have no physical meaning. I'm just going to fit you the data and hope that what works here is also going to be able to tell me what happens here. But that, of course, is a challenge because the conditions are very different and because the physics are very different in this accelerated corrosion test than what happens over decades. So that's a problem. We do have, to a certain extent, or basically I always say maybe the best thing to say is that what we want at the end of the day is to replace this kind of empirical data fitting models by some physically based mechanistic predictions. And we do have one model in corrosion that is physically based and that it works very well. That is only valid for uniform corrosion. This is what's called Faraday's second law for corrosion. So this is basically you get a change in mass loss as a function of the corrosion current density, but also as a function of some physical parameters. So atomic mass, balance change, Faraday's constant. So these are numbers that we know. So if we sample here the corrosion current density at the time, we can predict the mass loss. And this expression works very well. We can calibrate that expression with a quick experiment, and we can see that it works out pretty well over long periods of time. So this works very well. But the problem, of course, is that this is only valid for uniform corrosion. And uniform corrosion is relatively well understood, but it's not what is behind these catastrophic failures. So we need to do something like this, but for more complicated cases. And we won't be able to have very simple algebraic equations. We'll have complicated systems of PDEs, but computers have gone a long way. So we want to take advantage of that to build this first generation of physically based models that finally allows us to predict corrosion, this long-standing engineering and scientific challenge. And I will emphasize 2 points. So I think if I go back to my first slide, I said this is a new phase field revolution. As I will mention before, I mean, all of you work in computational mechanics, you've been to conferences and seen that phase field has really exploded in a couple of fields. One is fracture mechanics, the other one is microstructural solidification or microstructural evolution. What I will show here is that it is also going to lead to a revolution in corrosion. So this is one of the elements of the picture, but there's 2 elements basically that I think gives us an opportunity for us computational mechanicians to develop models that are finally capable of predicting corrosion. So basically, the first takeaway that I want to say is that predicting corrosion failures requires to explicitly resolve the underlying physical processes. That is the problem. If we want to go from here to here, we need to embed the physics into our model. We cannot do any assumptions. We need to remove all these kind of fitting parameters. We need to minimize assumptions. We need to just deliver predictions like these ones that rely purely on physical parameters that have a clear physical meaning and that we can independently measure in a lab. So I believe that there's an opportunity now to achieve this. And this opportunity has been made possible for 2 reasons. The first one is that we finally have very powerful computational multiphysics tools. Because I said, okay, why don't we have computer models for corrosion? Well, one reason, as I said, is that we do experiments in a very different regime than in practice. But the other aspect is that this is a very complicated coupled electrochemomechanical problem. So you can see here that whenever you have this is a standard this sketch showing a standard stress corrosion cracking problem where you have basically a metal that is subjected to mechanical straining. That metal has a defect, could be a crack, a pit. That metal is exposed to an aqueous electrolyte, imagine of seawater. In that aqueous electrolyte, you have multiple ionic species that are moving around due to fluid flow, due to electromigration, due to diffusion. Then at the interface between the metal and the seawater, you have multiple chemical reactions happening. You have, for example, corrosion, so you have metal atoms detaching. You also have other chemical reactions that induce the absorption of dangerous species such as hydrogen. Then those hydrogen atoms will travel inside of the metal. It will attract it to areas of high hydrostatic stress. They will lead to damage, and then you'll get the fracture of the component, and so on and so forth. So there's many things happening here, many electrochemomechanical phenomena. All of them are important, and all of them are strongly coupled. So if you really want to capture the physics of the problem, the mesoscale physics of the problem, you need to capture all this phenomena. And the good news is that we know what are the PDEs that describe each of these physical phenomena. These are well established and well understood. You can see some examples here. So these are the equations for the behavior of the electrochemical behavior of the electrolyte. You have here surface reactions, the formation of material, hydrogen transport within the material. Again, all of these are quite well understood and accepted. And as you can see, all of these are also physically based. So if I look at, Nernst Planck, for example, you can see they have a transport due to fluid flow, diffusion, electromigration. And you can see the predictions depend on diffusion coefficient, Faraday's law, temperature, conductivity of the material. Everything depends on very clear physical parameters. We don't have any magic alpha, beta here that we need to fit to an experiment. All of these are parameters that have a clear physical meaning that we know before we run our simulations. So there's no calibration with experiments. Before I run a simulation for a given material, I know what those numbers must be. And I think the key point is that we finally have enough computer muscle, and significant work has been going on in our community to develop robust multiphysics coupled solution schemes. So our computers are big enough that, I'm highlighting here in blue the degrees of freedom of the system. So you may end up with 10, 15 degrees of freedom per node if you're solving an aqueous electrolyte with many ionic species. But we have computers that now we can solve problems. I mean, I guess this was maybe unthinkable 10 years ago, but now we can solve problems with 10, 15 degrees of freedom per node. So we have enough computer power, and this is great news. But there's also been a lot of work going on in our community in developing very robust and efficient schemes for solving these couple problems. And I'll say a few examples from my group later on. But again, there's a lot of people working on this, either for batteries, for corrosion, and for many other couple problems. So that is one piece of the puzzle. So I think there's an opportunity to develop the first class of mechanistic models for corrosion. And the reason why we have this opportunity is because of two things. The first one is that our computers are big enough and we can solve couple problems. So we don't need to make any assumptions. We can resolve the physics as they happen in reality, right? Brute force calculations, so to say. The other issue, of course, or the other challenge is that this picture is, in reality, is not stationary. This defect, this speed, this crack is going to be evolving in time. And as this thing evolves in time, all of these things are going to be affected. So it's a complex multiphysics interfacial problem where we have an evolving interface and we're capturing the morphology of that evolving interface is critical. You can see it here, by the way, in an example related to an offshore wind turbine monopile. And in fact, corrosion fatigue, so what you see here in offshore wind turbine monopiles is the reason why these monopiles need to be retired after only 25 years. So we are actually working with wind turbine operators to develop more mechanistic models to see if they can extend the lifetime of these structures. But anyway, what you see here is a typical example. So you have a metallic structure exposed to an aggressive environment, in this case, seawater. And as you can see, first you generate those speeds. Then those speeds start evolving in time, and eventually you get the speed to crack transition and the propagation of these corrosion fatigue cracks. And again, very strongly coupled problem, and where we need to capture very nicely this morphology, because how this morphology evolves, how those speeds grow, is dependent on the local chemistry and mechanics, but at the same time, the local chemistry and mechanics themselves are dependent on the shape of those speeds, right? So if you have a sharper peat, of course, you're going to have higher stresses and lower pH and so on and so forth. So everything is very strongly coupled. So I need to be able to do all of this while this interface is evolving. And this is, I think, one of the main reasons why this has been a big obstacle for us computational mechanicians. And people have tried with level sets and other techniques, but we have been able to get somewhere, but not as far as we needed. And let me show you a little bit of the complexity of the problem. So my whole presentation is going to be a bit high level, but I'll say a few mathematical details as well. And of course, feel free to ask me after my talk. So the first thing that I'll share is that if I want to reproduce corrosion, the simplest mathematical model that I could use to reproduce corrosion will be one like this, where I have a normalized concentration of metal ions, which is equal to 1 in the metal, and then it becomes 0 far away from the metal in the electrolyte. And if I want to then describe what corrosion happens, I can have two situations: activation control corrosion or diffusion control corrosion. If I am under conditions of activation control corrosion, then the evolution of the pit, the velocity of the pit is given by this equation, which is again Faraday's second law. So you have the current, the concentration of the metallic ions, and then the concentration of the metallic ions in the interface is given by this Rankine-Hugoniot condition. But then if I have diffusion control corrosion, so if I saturate the number of pits on number of ions in my interface, and we need to wait for those ions to move away within the electrolyte, then the velocity of the pit is given by substituting the saturated concentration, the Rankine-Hugoniot condition, and the concentration of metal ions in the interface is given by the Dirichlet boundary condition. And what I want to say here is that this is a very complicated mathematical and computational problem, because we have an evolving interface that we need to keep track of, that has a complex morphology, and where we have changing boundary conditions, the Dirichlet, Robin boundary conditions, that are changing in time and space. So this is really complicated nightmare. I mean, I'm used to dealing with other interfacial problems such as fracture mechanics, but nothing surpasses this. This is really a computational nightmare. And I think this is where phase field models give us an opportunity to tackle this. Because, well, phase field models are very compelling when dealing with interfaces. Hopefully most of you have heard about them before, but if not, the idea is quite simple. So whenever you have an interface, you can describe that interface between these two phases as sharp and discontinuous, or as phase field methods do, you can smear that interface over a finite domain and use an auxiliary variable, the phase field, to describe where your interface lies. And this implicit representation of interfaces has many computational advantages, because then you just need to define a differential equation for the evolution of the phase field. And in essence, you can capture any computational problem, any interfacial computational problem, no matter how the complexity is. And this is, well, some advantages that come as a result of this is that, you define the interfacial equation in the entire domain. So there's no need for any special treatment, no need for moving chemical boundary conditions, because topological changes such as divisions of merging of interfaces are naturally captured without any ad hoc criteria. And also, important here, you can very easily couple this interface equation with equations describing all the physical phenomena. So it's very well suited for multiphysics problems. And as I said before, phase field has been a revolution in many areas of science and engineering. It is, by far the most widely used technique in solidification and microstructural evolution. This is where it all started. It has become extremely popular also in fracture mechanics. You can see this. You can see here why. This is hydraulic fracture, and you can see that very complicated cracking patterns can be captured in the simulation: crack branching, nucleation of secondary cracks, coalescence of multiple cracks. And I don't know if this is the dominant technique in fracture mechanics, but it very quickly becoming the dominant technique. It was this summer at USACM in Vancouver, and it was remarkable the amount of phase field fracture talks that I could see there. But our point is that the same way that phase field has revolutionized these two fields, there's an opportunity for us computational mechanicians to achieve a similar revolution in the area of corrosion. And as you will see later, this is an emerging field. It has started only a few years ago, but it's growing quite rapidly, and I think this is the time to ride the wave. So basically, what I want to present you today is kind of an opportunity. I'll show you that it's very easy to jump into this wave, and that this is a very good moment to tackle this important problem with these techniques. So how does it work? Again, I'm not going to get too much into the details. I summarize a little bit the state of the art in this recent review paper. But the idea is that similar to other interfacial problems, the phase field is going to describe the evolution of the corrosion front. So the phase field is going to describe material dissolution. So it's going to be equal to 0 in the aqueous electrolyte, equal to 1 in the metal, and then varying smoothly in between. So now we have that concentration and that phase field variable. And this is the simplest corrosion model that I can think of. There's other elements. Mechanics plays a role, for example, but I'll discuss those later on. The only thing that I want to say, I'm not going to get into the details of how you derive this. If someone is interested, everything is based on a free energy functional, so everything is based on thermodynamics, similar to other phase field models, right? So it's not similar, it's more similar to those using microstructural evolution than those using fracture mechanics. But again, similar to those phase field fracture models. And basically, in the simplest version, you have a system like this. So you have an Allen-Kahn type of equation, and then you have a Canhillier type of equation without the gradient, basically. So an equation for the evolution of the phase field, and an equation for the evolution of the concentration of metal ions. Again, in the simplest form. And then you can make some constitutive choices. Most phase field corrosion models are based on the so-called KKS model. So you assume thermodynamic equilibrium between the solid and liquid phases. But basically what I want to say here is that you end up with two equations like this. An equation for the source rate interactions. So the phase field equation, which is basically simulating material dissolution, so the detachment of metal atoms. And then another equation for the long-range interaction, which is the transport of metal ions. So, and you can see here basically that these two equations depend mostly in these two parameters. So the mobility coefficient L and the diffusion coefficient D, and both have a clear physical meaning. So D is a diffusion coefficient, we can measure very easily in experiments, and L, as you can see here, this mobility coefficient, you can see that for a case of activation control corrosion is proportional to the corrosion current density. So you can run a very simple experiment in 1D under activation control corrosion, and then you can correlate that mobility coefficient with your corrosion current density. Let me show you how this works. I'm going to start with a very simple example, the simplest I can think of. This is a classic benchmark in the corrosion community. It's called the pencil electrode test, and it's very simple because you effectively have 1D corrosion. You have a metallic bar that is corroding in basically in one direction, so it's effectively 1D. And you can see how it works here. So on the left, you are seeing the evolution of the phase field, the evolution of the corrosion front. You can see how the metallic bar is corroding. And then on the right, you see the concentration of metal ions all the way from the saturation concentration to 0 far away from the electrolyte. And the good thing is that because this is a simple 1D problem, we have an analytical solution for the case of diffusion control corrosion. So we can compare the outputs of the model with that analytical solution, as you can see, agrees very well. We have also compared with experiments and agrees quite well. But one aspect that I want to emphasize is that these models can capture naturally and very nicely the transition from activation control corrosion versus diffusion control corrosion that I discussed before. And you can see this here. So this mobility coefficient, as I ramp it up, as I increase my corrosion current density, I go from the linear behavior of activation control corrosion to the parabolic behavior of diffusion control corrosion. And then this means that when I'm in this regime where the corrosion current density is high enough, then of course my predictions are going to be quite sensitive to the diffusion coefficient. So this is another takeaway. I mentioned before, we have very complicated boundary conditions changing in time and space. We don't need to worry about those. All those phase corrosion models can naturally capture the transition from activation to diffusion control corrosion. But of course, I don't want to focus on 1D problems. Most corrosion failures are not 1D. We don't need advanced computational methods for handling 1D corrosion. What I want is to capture the complexity of corrosion. And corrosion can be a very rich and complex problem, but these techniques are quite robust and sophisticated. And as you can see here, it allows us to capture all the complexity that comes into this model. So we can capture, for example, the role of secondary phases, how the corrosion front evolves to those insoluble secondary phases. I can capture the role of pit interaction without any arbitrary or ad hoc criteria. I can also capture intergranular corrosion. And of course, these simulations can be done in 2D and 3D. In fact, we have now recently compared our predictions with some new XCT synchrotron observations, and we have allowed us to rationalize some interesting observations that were made with those synchrotron measurements. So this is a powerful tool not only to complement experiments, but also to replace experiments. No matter what is the complexity of the model, 2D, 3D, interaction of multiple pits, very complex corrosion front morphologies, the tool can handle it. But what's most important is that not only we can produce beautiful colors, but we can also do that incorporating the physics of the problem. We can again resolve by brute force all the physical ingredients that come into place. And when you talk to corrosion scientists, they tell you, Emilio, corrosion is a too complicated problem to be simulated with computers. There's many factors playing a role. All of them are interconnected. It's simply too complicated. And they are right to a certain extent. Corrosion is a very complicated and rich problem. But all that complexity can be incorporated into this framework. At the end of the day, these are continuum level finite element models. We know how describe the electrochemistry of electrolytes in continuum level models. We do that in batteries all the time. We can incorporate that into the model. We know that microstructure and isotropy also can play a role. We do crystal plasticity all the time in finite elements. We can easily incorporate that as well. We can incorporate the role of mechanics. We're always solving mechanics problems in our finite elements analysis. We can also combine this with simulations dealing with hydrogen ingress and embrittlement. We have been also working for quite a long on this area, so we can bring this on board. We can also capture corrosion product formation. So whatever comes to your mind, any problem that you can think of, it can be incorporated into this model. As long as it's a mesoscale problem that can be described in continuum mechanics, we can bring it into the model. So I think there's a great opportunity here and a very rich area to explore. And we've tried to, touch on some of these areas. By all means, this is all very preliminary work, and this is the very beginning. I'm sure there's many things to improve. But what I want to say is that there's an opportunity now to finally resolve the physics of corrosion and therefore deliver predictions that are mechanistic, that do not rely on fitting parameter or assumptions. So let me tell you how we incorporate some of these ingredients, and I will finish hopefully in time with just some of these examples. The first thing that I want to say is that, of course, we want to incorporate the role of mechanics. We're mechanicians, so we like mechanics. And mechanics can play a role in corrosion in two ways. Mechanics can influence corrosion by first enhancing the corrosion fields. This is, as you can see here, captured by Goodman. So corrosion kinetics, this is the corrosion current density, and enhanced by dislocations and hydrostatic stresses. And because the mobility coefficient is proportional to the corrosion current density, as explained before, we can enrich the description of the mobility coefficient and incorporate this interplay with mechanics. And then, we solve a mechanical problem as well, and we're able to predict what's happened. And we're going to benchmark our predictions with this C-ring experiment where you can see corrosion behavior as a function of the load. And here you can see the comparison with experiments, and you can see that, without touching anything, there's no fitting involved in here. We can capture very nicely the prediction for two different levels of applied load, and not only in terms of the intensity of the corrosion process, but also in terms of the corrosion morphology. So here you can see these two images on the same scale. There's multiple pits in here. We focus on only one pit, but one can model multiple pits, and you can see that the morphology of the main pit is quite similar. The other way in which corrosion interferes with mechanics is this so-called film rupture dissolution repassivation mechanism. So what do we do when we have corrosion problems? We use corrosion-resistant materials such as stainless steel. And then what will happen is that you will generate a layer that will protect you from corrosion, but this passivation layer is ruptured due to mechanical straining, and then you enable localized corrosion, pitting, and stress corrosion cracking. And this is, of course, a challenge. How to predict when the layer is going to rupture, we're going to have this localized corrosion phenomena. And we know what happens quite well. So we know that, as you passivate a layer into the metal, you are lowering your corrosion current density. But then eventually, when your strains are large enough, then you rupture their corrosion current density, and then you enhance corrosion kinetics. And then after some time, you start generating and repassivating the layer again. So basically, it's a cyclic process, a competition between repassivation kinetics and mechanical straining kinetics. And again, we can very easily incorporate this model into our framework because we can enrich again the mobility coefficient. We can make it a function of the corrosion current density and also the mechanical fields. We're solving a mechanical problem, so we know when we reach the critical failure strain of the passivation layer. And once you do that, then you can capture, again, you can resolve this interplay between corrosion kinetics or dissolution kinetics and repassivation kinetics and straining kinetics. And you can see that we can reproduce typical results expected from the experimental literature. And we can capture naturally this pit to crack transition that the community has been trying to capture over decades. Another important effect is, the susceptibility to microstructure. So we know that corrosion rates are sensitive to crystallographic anisotropy. So we can enrich the definition again of this mobility coefficient. We can solve an electrochemomechanical problem with Butler-Volmer kinetics, and we can define a grain orientation dependent corrosion potential. And when we do that, many possibilities open here. Of course, you can combine this, for example, with EBSD images that you take from your lab, with all your favorite crystal plasticity model, and you can learn a lot about, what role does microstructure play, because we're interested not only in the mechanical anisotropy, but also on the corrosion anisotropy. And we have ourselves tried to focus on these three aspects here. So first, we wanted to map regimes of microstructural influence. So we can run simulations with different combinations of RBEs, of grain sizes, and we can build maps like this, where we have some measure of, over potential of the environment and grain size, and we can map over which regimes we can handle well with an isotropic model, and over which regimes we need to resolve the microstructure of the problem. We've also learned that corrosion potential anisotropy dominates over mechanical anisotropy and grain size effects, and we can also use this to understand why 3D printed materials are more susceptible to corrosion due to the influence that the microstructure plays in this corrosion process. The other aspect is the electrochemistry, of course. Corrosion scientists will argue that this is a too complicated problem because there's so many things happen from an electrochemical point of view. And different to batteries, this is a bit more complicated problem because you need to solve for many ionic species. But again, we have now computers that we can handle this problem. So here we are in 10, 12, 15 degrees of freedom per node. But again, we can handle those problems now. So we can add the electrochemical behavior of the electrolyte and plant equations. We can solve for the electrostatic potential distribution. We solve this one for any relevant ionic species. We solve the chemical reactions, and then we can capture the role of the environment. So we can see, as we expect from experiments, how you change the solvent concentration, how it's going to change the peak depth. We can see the sensitivity to the applied potential, and we can see basically how that how the electrochemistry of the electrolyte is evolving as your corrosion pit or your corrosion front is evolving. You can capture that naturally. You don't need to make any assumptions on how much it changes and so on and so forth. You can see, depending on the pit geometry and the fluid flow and all the elements that are taking a role, how these things naturally evolve. And one thing that I want to emphasize here is that when you're solving all of these surface reactions, these are very nonlinear problems, and we often have convergence issues here. And a typical commercial finite element package for this kind of multiphysics problems is COMSOL. It has implemented most of this electrochemistry, and it's easy to, it has already some facial fracture models, and it's easy to incorporate facial corrosion in them. But we saw that we're very limited when simulating these corrosion reactions because they're very nonlinear and it's quite difficult to solve. So we created we decided to tackle this problem with our own in-house codes, and we decided to use LAMP integration as opposed to Gauss integration. And what I want to say is that we were able to bring very significant reductions in computational time. So just to provide you an example, we were looking at a case study where we're trying to predict how much hydrogen comes into the metal due to those reactions that are happening there. And with COMSOL, we were able to solve after a week in our supercomputer, we were able to predict what happens after 10 minutes of exposure to this corrosive environment. When we implemented this LAMP integration in our in-house C++ code and in the MATLAB code as well, we were able to calculate over the same time what happens over 50 years. So we went from 10 minutes to 50 years. And 50 years is, the engineering time scale that we're after. So what I want to emphasize here is that there's many opportunities for people like us. So a lot of people from, you know, the corrosion science community that do not have a computational mechanics background are jumping into this problem, are jumping into this opportunity, and are using commercial finite element packages like COMSOL. But I think there's an opportunity for people like us to make a difference, because we can go much beyond what commercial packages allows in these cases. And we know a lot of tricks from our standard, I would say, conventional computational mechanics problems that we can bring into this discipline. Okay, another application that I really like is what I call biocorrosion. So this is the degradation of biodegradable materials in body fluid. And here the motivation comes from the fact that whenever we have an implant in our body, we normally use titanium or materials that do not degrade. And that's a problem, of course, and particularly for kids, because then you need to do a second surgery to remove the implant. So the ideal material that we want is a biodegradable material such as magnesium that remains stiffness throughout the tissue or bone healing, but then eventually degrades into the body. And magnesium is perfect for this, except for one thing: magnesium degrades too fast. So there's a lot of experimental work going on in trying to develop, you know, magnesium-based solutions for this, where maybe you change the geometry of your implant, you change the corrosion kinetics, or maybe you alloy magnesium with other materials, or you come up with a composite that contains magnesium and other biodegradable materials to try to slow down this process. But this is, as you can imagine, a very slow process, and it requires a lot of trial and error. So our goal is to develop this kind of phase field models for corrosion applicable to this degradation in body fluid. In that way, we can accelerate the discovery process of this new generation of magnesium alloys. Two aspects that I want to emphasize here. The first one is that we're not limited to simulating small samples. We can handle, as you can see here, 3D simulations of stents and full implants. But the other aspect that I want to emphasize is that one of the problems here with experiments is that you cannot do experiments on humans. So you need to somehow simulate that body fluid. But with these models, we can do virtual experiments in vitro conditions. We can show that the model agrees well with lab experiments, and then we can change the electrochemistry of the electrolyte to reproduce human body fluid. So we can go from in vitro conditions to in vivo conditions. Moving on, one thing that I'd like to say is that so far, I focus on cases where you're applying a current or an applied potential. And this is what commercial finite element packages like COMSOL will allow you to do. But again, when we have our own tools as computational mechanicians, we're not limited by that constraint. So we can simulate what happens not only in lab conditions, but also what happens what we call in natural corrosion. So in lab conditions, we enforce an applied potential, an applied current, but in natural conditions, you have charge conservation. Your metal is degrading, without any applied potential. So basically, you can do that. You can add as a degree of freedom the metal potential, and then you enforce charge conservation. This is a code that we develop in MATLAB, and we also have it in C++. And we use this, for example, to understand what happens when you have reinforced concrete structures, to understand under which conditions, for example, how much water you need to have to sustain the corrosion process, and other interesting problems. You can see that more details on the paper. We have also used this to tackle that problem that I showed you at the very early beginning, going all the way from those accelerated corrosion current tests that we do in the lab to predicting what happens over decades. And because we can capture the kinetics of the problem, the physics of the problem, we can show that it's very different from that linear interpolation that I showed you before. But we can capture what are the rate limiting phenomena. We can capture the transitions from one mechanism to the other. And we can go from those fast, impressed corrosion current tests in the lab to predictions over realistic time scales. And this is work mostly done by my student, Eugen Korek. We can also incorporate the role of the electric double layer. I'm not going to get into details for the sake of time. There's some literature there to show. But I'm just going to finish with what I think is a very interesting example, which is going towards a generalized model for stress corrosion cracking. So stress corrosion cracking, again, is a very complicated problem. It's because not only you have anodic dissolution, material detachment, but you also have fracture that is originating due to mechanical rupture, but typically accelerated due to the ingress of species such as hydrogen. So it's a complicated problem, and you need to think you need to make an assumption before you model on what is the dominant mechanism. But the good thing about these models and computers being big enough is that we don't need to make any assumptions. We can simulate everything into the model. We can become greedy. We can add all the ingredients and let the model decide for us. So you can see here, we are now combining everything that I showed you before. So your mechanical problem, the ionic transport, electrochemistry, and corrosion, with also the fracture problem. So we have a phase field model for fracture, and also the hydrogen uptake and transport problem. So we're solving everything up there. And then when you do that, basically you can capture naturally what is the the impact of the environment you can capture naturally, whether it's anodic dissolution or hydrogen-driven mechanisms, and one combines with the other. And there's a few items, of course, that one has to take into consideration. The first thing is that you need to be able to capture well what is the crack opening. So there's some ongoing discussion in the phase field fracture literature and various approaches to capture the crack opening in your to capture appropriately the crack opening. This is something that people working in hydraulic fracture are very interested in, but it's also relevant here. We need to understand well the electrochemical behavior inside of cracks, and we propose a solution that you can check in our recent CMME paper. But also we can capture, basically what this means is that at the end of the day, you have a model that without any assumptions, just providing the model with the material, the environment, and the loading conditions, can capture the failure. And you can see here that it agrees pretty well with experiments over a very wide range regime, all the way from the cathodic regime where hydrogen dominates to the anodic dissolution regime. And we use this model to understand also the classic experiments by Gruhl. These experiments were done in the 80s, and he was trying to understand whether aluminum alloys will fail due to corrosion or hydrogen embrittlement. So he did some very clever experiment where he exposed some cylindrical samples to a corrosive medium. He protected the outer surface, and he said if failure initiates from the inside, this means that it was due to corrosion. If it's near the notch, it's due to the hydrogen that is traveling through that towards the stress concentration area. And we saw that with the model, we are able to predict quite nicely their experiments. I think his experiments fail after 11 hours, and our simulations fail after 11 hours and 20 minutes, if I remember well. And then we can also change the conditions, change applied current density, and see what he would have predicted if we had considered all the different conditions. That's all. I'll just finish hopefully on time with a few questions. Again, the points that I want to emphasize here, and the reason why I wanted to present this work is that I think there's an opportunity for us as a community. I think that corrosion is a long-standing problem for scientists and engineers. There's a lot of money involved in corrosion, and there's a lot of people interested in solving this problem, in predicting corrosion failures. And we are not able to predict corrosion failures. Again, they happen every day, everywhere in the world, despite years of experience. And the reason is that we lack reliable models. I mean, we lack models altogether, but ideally we want models that are mechanistic, that incorporate the physics of the problem. And I think that there's an opportunity now to do that, because we can finally resolve, kind of by brute force, explicitly resolve those physical processes that govern corrosion. So we don't need to make any assumptions. We can deliver predictions that rely on diffusivity, on Faraday's law, on temperature, on parameters that we know, that we measure, and that we know beforehand. There's no fitting, there's no calibration involved. We know beforehand what are the numbers that come into our model. And I think the opportunity has been made possible by this kind of coupled multiphysics modeling. Again, there's many people working on coupled multiphysics modeling in our community, mostly oriented towards problems such as batteries or hydrogels, for example. But I think there's an opportunity to bring those into this important area of corrosion. And I think the other recent development that allows us to explore this opportunity is facial modeling. There's many ways of dealing with evolving interfaces. Evolving interfaces are both, I guess, a challenge and an opportunity for computational mechanicians. But I think that, in my opinion, phase field has been really a life changer. And I think that in the same way that phase field has revolutionized fracture and solidification, is going to be a revolution in corrosion science. The good thing, again, is that the framework is very general, it's flexible. You can incorporate it easily into your favorite finite element code. You can capture naturally the activation between diffusion and activation control corrosion. You can capture problems of arbitrary complexity, bit interactions in 2D, 3D, intergranular corrosion, secondary particles. You can combine this with EBSD measurements, with crystal plasticity. So it's very straightforward to incorporate it into what you already have. So I think this is one of the key advantages of this method. And then, well, we try to contribute to this community, or we try to champion this approach by incorporating some aspects that we thought were relevant. I'm listing here some of them, but every time I talk to corrosion scientists, they come up with another 50 or 100 interesting phenomena that they want to incorporate into these types of models. And again, many opportunities for us as computational mechanicians to bring all the interesting acceleration schemes that we have developed through other applications into this problem, and bring all our computational insight into developing tools that not only can bring fundamental insight, but can also handle the complexity and the scales associated with engineering practice. That's all. I would just finish by saying that we release all the codes that we develop. So everything that I've shown you in this presentation today, you can reproduce at home. You can download the codes from our website. We work with a variety of techniques. So we have our own in-house codes in C++ and MATLAB that we also share. We also do a bit of work on Julia and Phoenix. But we also use commercial finite element packages as Abacus or COMSOL, so we provide all of those up there. So up to you, whatever you use, and if you have any problems, of course, feel free to reach out. Thank you very much for your patience, and hopefully haven't run out of time. Thank you.
Sam, thank you so much for the wonderful talk. It was lovely to hear the importance of the face building corrosion. As you said, yeah, corrosion is a multi-billion-dollar problem in the world. So, and I'm glad to see that at least a few computational mechanics folks, they are moving in that direction. So I guess now I'll open it up for the questions. Maybe I'll stop recording here so people, they can